That means, since they have the same kappa and they have the same epsilon 0, it means that A over D has to be the same for both capacitors. So A divided by D for this one must be the same as A divided by D for that one. But if D here is 100 times larger than this one, then this A must also be 100 times larger. Because A over D is constant. So if A here is 100, then A is here 1. But now think about it. What determines the volume of a capacitor? That's really the area of the plates times the thickness. And if I ignore for now the thickness of the conducting plates, then the volume of a capacitor clearly is the product between the area and the thickness. And so it tells me then that this capacitor, which has 100 times larger area, is 100 times thicker, will have a 10,000 times larger volume than this capacitor. And this baby is 4,000 volts, 100 microfarads. It has a length of about 30 centimeters, 10 centimeters like this, 20 centimeters high. That is about 10,000 cubic centimeters. 10,000 cubic centimeters. You go to Radio Shack and you buy yourself a 40-volt capacitor, 100 microfarad, which will be 10,000 times smaller in volume. That will be only 1 cubic centimeter. And if I had one of them behind my ear, you wouldn't even notice that, would you? Could you tell me what it says here? 100 microfarad, how many volts?
40.
40 volts. That's small. Compared to this one, which can handle 4,000 volts. But the capacitance is the same. So you see now the connection with area and with thickness, by no means trivial. All this has been very rough on you. I realize that. It takes time to digest it, and you have to go over your notes. And therefore, for the remaining time, we have quite some time left, I will try to entertain you with something which is a little bit easier, a little nicer to digest. Professor Mussenbroek in the Netherlands invented, yeah, you can say he invented the capacitor. It was an accidental discovery. He called him a Leyden jar because he worked in Leiden. And a Leyden jar is the following. This is a glass bottle. So all this is glass. That's an insulator. And he has outside the insulator, he has two conducting plates. So that's a beaker outside. And there's a beaker inside conducting. That's a capacitor. Although he didn't call it a capacitor. And so he charged these up, and so you can have plus charge here and minus Q on the inside. And he did experiments with that. The energy stored in a capacitor, we discussed that last time, equals 1/2 times the free charge times the potential difference. If you prefer 1/2 CV squared, that's the same thing. I have no problem with that, because this C is Q free divided by V, so it's the same thing. What I'm going to do, I'm going to put a certain potential difference over a Leyden jar. I will show you the Leyden jar that we have. You see there. And once I have put on some potential difference, put on some charge on the outer surface and on the inner surface, you can see the outer surface there. The inner one is harder to see, but I will show that later to you. So here you see the glass, and here you see the outer conductor. And there is an inner one too, which you can't see very well. Once I have done that, I will disassemble it. So I first charge it up, so there is energy in there, this much energy. And then I will take the glass out. I will put the outside conductor here, the inside conductor here. I will discharge them completely. I will hold them in my hand, I will touch them with my face, I will lick them, I will do anything to get all the charge off. And then I will reassemble them. Well, if I get all the charge off, all this Q3 goes away, there's no longer any potential difference. When I reassemble that baby, then clearly there couldn't be any energy left. And the best way to demonstrate that then to you is to take these prongs, which I have here, conducting prongs, and see whether I can still draw a spark by connecting the inner part with the outer part. And you would not expect to see anything. So it is something that is not going to be too exciting. But let's do it anyhow. So here is this Leyden jar, and I'm turning the Wimhurst to charge it up. I'm going to remove this connection, take this out, take this out. Come on. Believe me, no charge on it anymore. This one, it's all gone. Believe me. There we go. And now let's see what happens when I short out the outer conductor with the inner conductor. Watch it. That is amazing. There shouldn't be any energy on that capacitor. Nothing. And I saw a huge spark, not even a small one. When I saw this first, and I'm not joking, I was totally baffled. And I was thinking about it, and I couldn't sleep all night. I couldn't think of any reasonable explanation. And so my charter for you is to also have a few sleepless nights and to try to come up why this is happening. How is it possible that I first bring charge on these two plates, disassemble them, totally take all the charge off, and nevertheless, when I assemble them again, there's a huge potential difference between the two plates. Otherwise, you wouldn't have seen the spark. So give that some thought, and later in the course, I will make an attempt to explain this. At least that's the explanation that I came up with. It may not be the best one, but that's the only one I could come up with. In the remaining 8 minutes, I want to tell you the last secret, which I owe you, of the Van de Graaff. And that has to do with the potential that we can achieve. Remember the large Van de Graaff? We could get it up to about 300,000 volts. How do we charge a conducting sphere? Well, let's start off with this hollow sphere, which is what the Van de Graaff is. And suppose I have here a voltage supply with a few kilovolts. I can buy that. And I have a sphere, and I touch with this sphere, which is an insulating rod,